Hello, Peter here. In our last episode we created our getNearestPointLight function, and in this episode we're going to finish the PointLight feature. So let's open the SDL component, and we are going to create a new function called SetPointLight. But we need some variable, and we can do that first. Under SDL we have the PointLight radius correction already from the previous episode, but now we're going to add one, and that is PointLight multiplier. And again, this one has the same function as the directional light multiplier. It gives us some freedom to correct the intensity of the light. It is a float, and we want it in the SDL category, and we also want it editable. Really, I would like that on top of that one. So that the radius correction is under it. Alright, so let's create our new function. We will call that SetPointLight. Now this function will take a bunch of inputs. Most of them are the outputs of the SetNearestPointLight. So the very first one is our light itself, and that will be a PointLight object reference, and the second one is a boolean which is called last lit. And I will explain that later on in more detail. That input is going to be a boolean that tells us if in the previous call, in the previous SDL tick, this particular slot, because we're going to have two point light slots basically, has been lit or not. You will see that that is interesting information. The next one is lit, and that is an output from the getNearest that tells us if we are actually within the attenuation radius of the light that we are passing in here. And we also had a distance, and that is a float. And then we have the names of our two parameters, and that is going to be color parameter name, and we will make that a name. And we also have the normal parameter name. And that too is a name. So that are all the inputs set up. Now, there is only one instance, one situation where we're immediately done. And that is when we were not previously lit, this slot, this particular slot of the two possible PointLight functions, if that wasn't lit, and we are not currently lit by the nearest, in that case nothing needs to be done, but we need to write that out so that we can fix that. So let's do a branch. And let's say this last lit, if that one is false, we're going to do another branch. And then we test if the current lit, so the output of the get nearest point light, tells us if we are within the attenuation radius. If that also is false, then we can safely return from this function. So from there we just do a return. And the return node for this function only has one output. And that output is the out lit. And that is a boolean. Now the out lit can be different than the lit from the get nearest that comes in here. Because in this one, in the point light, we always need to do a trace, and we might hit something in the trace. Now to facilitate for the rest of the function here, I'm going to promote a few things to local variables. So the lit that we got in from the get nearest point light, I'm going to promote to a local variable, and we are going to set the value, and it doesn't matter from which of those two. So we can just hook them both in like that. The next one I want to promote is distance. So we can promote this one to a local variable. Oh, by the way, I forgot to set a name on this one. The name for it is internal lit. Well, that's at least what I'm choosing. Internal lit. That doesn't look good. Internal capital lit. Like that. And this one is the internal distance. Now we do this because we need them later on, and this network, the graph, is going to be very, very annoying if we do not promote these variables to local or these inputs to local variables. Same for the two parameter names. So we can say here somewhere promote to a local variable, and let's name that one something shorter than it is now, CPN. I think we understand what it stands for. And then this one too. And we're going to say NPN. Right. Okay, and then this light that we're having here, let's get the point light component, because that is something we're going to use as well a number of times. And let's promote that one to a local variable that we're going to call, simply point light component. Like that. So it's not a beauty, but it will make things much easier later on. Now the structure of this function is almost the same as our get or our set directional light. In fact, it is somewhat simpler because we do not need to choose between using a trace or not. We always need to do a trace. So what I'm going to do is I'm going to wire up the rest of this function for you, and then we're just going to talk about the differences and how these things here play into it, instead of you having to watch me wire up this this whole thing. So back in a sec. Okay, granted it was a bit more than a second, but let's see what we have now. From where we set the point light, we don't need to do any decisions. We're just going to do our line trace for object in the same manner as we did in the set directional light. So set trace complex, and here we have an array of the things, the object types, and I took the same ones as for the directional light. You can always add. Now the start of our trace is the world location of the object here. The end of the trace obviously is the world location of our point light, because we want to see from our object to the light if we have a clear path. So start and end, very simple. That's basically the trace done. Now if we have a hit, the return value is then true, then obviously we are not lit. So if it is false, we say a boolean not, and combine that with the internal lit. Remember, the internal lit is the output of the get nearest point light, and that tells us if we are in the attenuation radius of the light that we are investigating here. So if that one isn't lit, we are never lit. But combine them, and then we set internal lit to the result of the trace, basically. And then we simply set our two vector parameter values in our dynamic material. We give it the parameter names, the color parameter name and the normal parameter name, set them, and then return from the function returning our internal lit to indicate if we are indeed lit or not by this light. Now how do we get the normal? Well, that is also fairly simple and quite similar. We have our world location, and we subtract from our world location the world location of the point light. We normalize the difference, and remember to reverse the sign on it because we remove that from our material function, if you remember that. And that simply is then fed into the material. Now the intensity is slightly different, not a lot but a bit, because what we do is we get our point light component that we had as an internal variable here, a local variable, get the light color, and we then need to multiply that based on the intensity. So we also get the intensity that was configured. And based on internal lit, we either pick that one or 0. If we were not lit at all, all light is removed. Now instead of here, because we are dealing with point lights, and the light is not the same everywhere, the distance from the light is a factor. So what we're doing here is applying the inverse square rule. The intensity that is provided for a point light is like in lumen, you can say. So here it's going to be slightly physical. It's physics. The intensity is in lumen. The distance, however, is in centimeters. So what we want to do is to multiply that by 0.01 to make it meters. Now the rule is that the total emission of light, so which is the intensity here, divided by 4 pi times the distance squared, the radius squared really, gives us the intensity of that point at that radius, at that distance. So that's what's happening here. What it does is to create a natural fall off the further we come away from the light. I could have chosen just a linear fall off, but that is not really very natural. So I chose to implement the inverse square law here. Anyway, so when we calculate the square of the distance and correct it to be meters and then times 4 as well, multiplied by pi, and then we divide it by the total intensity, which is either the real intensity or 0, so this becomes or an intensity or 0. And then we still have our point light multiplier to adjust this, to play with this value, to make it just as we want it. Then finally we can multiply it with the light color and set that value in our color parameter. So that is basically it for this function. Yeah, I think so. So I will give us one last view because yeah, you couldn't follow it. So we had this one that was quite clear. And then we got the trace with the start and the end point, and from them we calculate the normal. Then we calculate intensity of the color using the inverse square law. And here we just set based on it being lit or not what internal lit is going to be, set our parameters, and return. Okay, let's compile this and save it, and we can close. No, we're not going to close really, because now we're going back to the event graph. So first we need to get the point lights array from our SDL level data. So let's get that one out. Then get the point lights. That was this one. And then we have to check if we actually have lights. So let's call length on it and then see if that is greater than 0. 0 is good. And then from here we can do a branch. Now, if this is false, we don't have to do anything. If it is true, we do have lights, and we are going to call our get nearest and set of the point lights. Now, the least confusing way to explain how it works is for me to first wire it up. That will be the easiest thing. So I'm going to do that very quickly and then be back. So I'm back. So what was it that I did? Well, I just moved this a bit down because we need to feed point lights into our get nearest light. Now, as you remember, the point lights, the array, is going to be internally copied to temp lights, and from that one the nearest is removed and returned. And that is the out point lights. And that is the array that we're going to pass to the next call to get nearest. And it will then remove the nearest from this one, and that will be then the second nearest light. Now you also notice that I created two Boolean variables, lit1 and lit2, and that is to keep the state of this kind of slot. It's about the parameters PL1 color and PL1 normal, and this little section sets the variable, the vector parameters PL2 color and PL2 normal. Now the problem is that between SDL ticks, it can well be that two point lights change places. What I mean by that is that, say in one SDL tick event, the nearest point light, which is then processed and set into PL1 color and PL1 normal, on another SDL tick event suddenly is the second nearest, because our object is moving. So then it will be processed by this bit. Now what we do not want is that the material parameters, the parameters for color and normal, still have the values belonging to another light. And that was also the bit in the SetPointLight where I checked if we had last lit, this one, and lit. So that the only safe way to exit doing nothing is when both of them were not lit. Otherwise you will get blotches of light remaining on your object if the lights just switch places or something. So that is a bit hard to talk about, but I guess you will see it, because these parameters are fixed, but the lights can change. So the same light can be processed by this bit and later by that bit. Okay, otherwise, when we have the nearest one, we pass that into SetPointLight. We feed it our saved last lit. We also feed it the lit from the nearest point light. That means, are we in the attenuation radius, and the distance to that light. Make sure that the parameters that you pass in, the names here, are exactly the same as in your material. Now then, the result of the SetPointLight tells if we are lit or not, and we save that one in lit 1 in this case. Lit 1, lit 1. And then we repeat with the new array to find the second nearest and do exactly the same thing. Only then for PL2 color and PL2 normal. And then again we set lit 2. So that is all we need to do. I hope this is clear. You can always ask questions about it in the comments and I will gladly answer them. So let's compile this. Oh, wait, one little thing. Let's check that point light multiplier. Yeah, make sure it has as a 1 there. I did that just now, but I forgot to mention it. So make sure the default value for point light multiplier is 1, because before I did this, I left it at 0, so that's not good. Then you will, if you not think about it, you will not understand why the light isn't working. Okay, compile. Save, and now we can test it. Okay, so let's look what we have. Let's see if our properties are there. Yeah, point light multiplier and the radius correction. Remember, this one is in percentage, positive or negative. Okay, how are we going to test this? I got tons of spotlights everywhere. Yeah, but I don't have any point lights. So let's add them. Let's just add a light here. That one is pretty close. And let's add another one. Where is that one in relation? Put it a bit more to the side here. Yeah. Higher maybe. Now be sure that you put the lights to static, because that is what we have in mobile platforms, and also then you won't get annoying shadows, because even within lit as a material they still seem to cast shadows. So now that is all gone. I'm not going to rebuild light because I'm only interested in what happens with our sphere here. Let's just see what happens. Oh yeah. One little thing, maybe in the sphere, just to make it more clear, let's remove the ambient light and receive directional light so that it's only those 2 point lights. Good. That looks great. Now, and indeed you see from the debug trace lines where the lights are, and it gets lit by both these lights. So just give it a little push, you will see that it's completely dynamic, of course. And when it gets too far away, when it's outside to the attenuation radius, it switches off. And you see there is a nice natural fall off of the light, which is the inverse square law. Awesome, this works. I'm happy with that. So you can play around with the values by making it lighter and also set more sensitive, correcting the attenuation radius. But for now I think that's enough for this episode. Hope you enjoyed it, and in the next episode we will go on with spotlights, which at least will be easier to test. So see you then. Bye bye. Hello, Peter here again. Just wanted to say thanks for watching this video. Please let me know what you thought of it in the comments. Below there are links to other episodes in the series, and don't forget to subscribe so you are the first to know when the next episode is up. Thanks again for watching, and see you in the next video. Bye!